Welcome back to the Architecture Weekly YouTube channel. Today we have a special occasion because I'm interviewing Vladik Khononov about his new book, Balancing Coupling in Software Design, right?
Here is. Yeah.
Yay! Hooray! And we're not only just doing an interview and asking questions. Alexa, lights on. Okay, that's much better. But we also distributing the vouchers for the free ebook. So we were gathering the questions to Vladik for the past couple of weeks, and we actually three winners. But we will get to know them only at the end of the interview, like in 50 minutes. So listen carefully and let's start. Vladik, welcome.
Thanks so much. Thank you for inviting me.
Really happy to discuss your new book. So first of all, congratulations on doing this. So I understand that that's a huge effort.
Yes, I lost a lot of hair in the process.
Okay. Hopefully you will be able to regrow it. All right. Let's jump right into the questions. So the first one I get is what actually inspired you to write a book on this particular topic?
That's a good question. So this story of my fascination with coupling started many years ago. It was it was around 2006 or 7, and back then I remember going to a local meetup. It was called Software Craftsmanship Tel Aviv, if I remember correctly, and there was talk about coupling and cohesion, and that was probably one of the first time I was really exposed to these topics. And I was thinking, wow, that's really interesting. And I also remember that at the end of that meetup, I couldn't really understand what cohesion is. Like, okay, I get that coupling is something bad that we always have to avoid, but what is that cohesion, the good thing? How do we measure it? How do we achieve it, etc.? Anyway, then I've forgotten about it for a few years until in 2000, I don't remember what year it was. But during the hype, the microservices hype, it just started. Everybody was talking about microservices. So back at the company that I was working at back then, we decided to give this architectural style a try. We tried. We tried to do everything that people were suggesting at blogs, conferences, etc. And that was such a spectacular failure, that project. It was like take everything that they promise that microservices will get you, and we got the complete opposite, like disaster. And I wanted to understand why. Why have we failed back then? And I found the answer to that question in a very old book from early 70s. It was called Composite Structure Design. And the chapter that I found the answer in was called coupling. And then I said, okay, I have to understand this topic, coupling and cohesion, because it is really important. And it ended with this book.
Okay, so this story began many years ago, and actually with some failures. So there were an actual need for your job to understand those terms.
Yeah, exactly. So I had to understand this notion of coupling, how it affects design decisions, how it affects the outcome of a project. And in the process, as I mentioned, I found the first answer I found in a very old book from 70s. And then I started discovering more pieces of that puzzle in other books that unfortunately we have forgotten nowadays. So in order to apply it in day to day, not only by myself, but also by other people in the company, I had to adapt it to our modern realities, how we're developing software nowadays. So adapted that forgotten knowledge to our current realities. That's how the model of balanced coupling came into being.
Okay, so you actually dig up some old ancient manuscripts to bring it to the modern reality.
Yeah, yeah. It's stuff that we already knew a lot of time ago,
Mm-hmm.
but unfortunately, first of all, we have forgotten about that, and second, we couldn't just go ahead and apply it nowadays because some of the models that were used back then in 70s, they were based on programming languages that are not really common nowadays, like COBOL, Fortran, and other fun stuff like that. So some adaptation it was really needed. So yeah, that's
Okay, yeah. Thankfully, we already have it. So thanks a lot. How long did it take to write the whole book?
so it took me about 3 years to
Oh my God.
formulate the no, wait a second. 3 years to formulate the model, to test it out in day-to-day work, in to see what form of that model is the most effective one to, to use, not only to use, but also to explain to other team members and get them on board. So that took 3 years, and writing the book, oh my God, it's 5 years. Now,
Five years of writing a book. How does it happen? Like, do you have some kind of routine that you get up in the morning and you're like, I need to write two pages today, or like how it happens?
yeah, so the most important part of the process is to acknowledge that I'm a software engineer, first and foremost, and that gives me the green light to miss deadlines. So that book was supposed to be published 3 years ago. Yeah.
Okay.
So it is late by quite a lot. Um, my routine is for this book was to write a technical draft,
Mm-hmm.
a draft that only outlined the technical ideas, like no storytelling. My goal wasn't to make it readable or stuff like that, just to outline the technical stuff and hear the feedback from reviewers. Now, that draft was so bad, like people couldn't finish reading it because I said there are not going to be any storytelling there, and it made that draft really hard to read. So
Mm-hmm.
eventually, when I received green light for the technical stuff, I had to rewrite the book, and I had to rewrite it not only once, but there is one chapter on modularity. It was rewritten 7 times from scratch. Um, yeah, so that's how I missed those deadlines.
Seven times. It's like
Yes.
looks like writing a book is even worse than writing software because you can rewrite like software one time, maybe two, but the like, 7 times that's incredible.
Yeah, that's quite a punishment, to be honest.
Yeah, but does it work in the end? Like, I mean, you come up with a solid piece. It's like easy to read and it's useful and it has the practical advices, right? In the end.
So the moment I sent the final manuscript to the publisher, I said, okay, I don't want to see it never again. I don't want to think about it. I want to forget it like a bad dream. But, when you get positive feedback and people are saying that this book helps them in their work, then yeah, of course, tell
Yeah,
myself, okay, it
I
was
mean,
worth
you
it.
even agreed for an interview, right? So like, it's impossible to forget now.
Yeah.
Okay, there's a question in the chat actually, so folks feel free to ask questions. Did you leverage AI in the process of writing it in any way?
Course, of course. Now the problem is when I started working on the book, AI was in its early stages. Not AI, but you know what I mean. GPT models, LLM
Yeah, yeah.
models. And back then I tried, I was thinking to myself, okay, so we have that text completion API by OpenAI. Let's see. So here's the chapter on coupling and complexity. Please write it for me. It was terrible. Now, I have leveraged AI for, first of all, proofreading.
Hmm.
I'm not a native English speaker. For me, English is not even a second, it's third language, so it helped me a lot. Anyway, we have those people that copywriters and editors working for the publisher, and they said, okay, it sucks, let's rewrite it again. And they wrote their own version. Um, another another part of book writing process that I tried to offload to AI was those poems that started each chapter. Initially, it started as a joke, but at some point I said, okay, I really need these poems because it gives me another way to summarize the material of each chapter in a
Hmm.
way that is kind of easy to read and is somewhat easier to remember for the readers. So I imagine myself reading the book, and before getting into a chapter, I have that short poem that kind of explains what I'm about to learn.
Yeah, yeah, yeah. So for the folks who didn't read it yet, that's actually a nice piece of the poem. So, balancing coupling, chapter number 10, starts with a change in the east echoes in west. Software design is like a game of chess. Near or far, how to balance the ends. As consultants proclaim, it depends.
Now, I tried to make ChatGPT write those poems. It didn't work. At the end, I had to intervene to make them really, really connected to the material of each chapter. So I would say that each poem you're reading is written in collaboration. It's 50-50 effort.
Okay, okay.
50% AI, 50% myself. No, 33% LLM, 33% myself, and 33% Red Bulls. Lots and lots of Red Bulls.
Red Bulls. Okay, okay. I will contact them after the interview and ask for the sponsorships. So yeah. Okay. Thank you very much. Okay. Let's start discussing the coupling itself, right? The material the book is about. So the book actually starts with coupling, and you argue that it's impossible to build any useful system without coupling in the first place. Can you explain why?
Yeah, so the book is structured in such a way that first I want to get an agreement with the reader about what is coupling. Is it something that is necessarily bad, something that we have to avoid and always try to decouple everything and destroy that coupling everywhere? And the thing is, if you go to the basic definition of that word, it's not something negative.
Mm-hmm.
It simply means that you have a number of components in a system that have to work together. They're integrated somehow. So we have coupling, we have that connection between them. Now, whether that connection is good or bad, that's a topic of other chapters. But at the most basic level, coupling is about connecting things. Now, if you have a system, and a system by definition is a set of components that are working together to achieve some overarching goal, then without connections, without coupling, you won't be able to achieve that overarching goal. You will get only a bunch of components. To get to make the sum of those, the value of those components, the value of the system greater than barely the sum of the components, you need those interactions. You need that coupling. You need them to be integrated in order for the whole system to work, to achieve something that each component individually cannot achieve. And so yeah, that was my point about coupling.
Yeah, I mean, every developer, when they write code, they call some functions from other functions. And when
Mm.
you have this connection, you essentially have the coupling. And you write several chapters on like different types of coupling that we can have in the system. But essentially, what you say, as I understand it, is that without coupling, you actually cannot build anything that brings greater value than just the set of components.
Yeah, exactly. Yeah, that's the point.
Okay, so basically, coupling is an emergent property of the system. It's essential nature, right? So we cannot have systems without coupling. And the question then will be like how we should manage this coupling, right?
Mhm. Yeah. Now we have those connections, but we can design those connections between components of a system in different ways. Some of those ways are going to work for us. Some of them is going are going to work against us, right? So we have to really drill down and understand what's going on. Let's say that we have two components and a line that connects them. So what is going on in that line, that pipe? And here things are getting more complicated than simply saying coupling is bad, cohesion is good.
Mm-hmm.
We really need to understand how that coupling is designed. And there is no way, at least I haven't found one way to simply look at that integration and give it a grade, whether it's good or bad.
Okay.
It's more complicated.
But when I was reading, I was always thinking about this business orientation because we like occasionally we write software for fun, right?
Mhm,
And there's a separate discussion about that. But the majority of the software we create is to serve some purpose, some business purpose, right? To solve a business problem with the software. And that was like while reading, I was always wondering, okay, so this type of coupling, how can I weigh it in if I have an appropriate type of coupling for a particular business solution? So how do you understand it as a software developer?
mhm. Yeah, so to answer that question, we have to get into the three dimensions of coupling. And that's where things are getting complicated. So whenever we have those two components, in order to be able to work together, they have to exchange some knowledge about each other. Say you have a microservice and I want to use it. In order to use it, I need to know a few things about it. Maybe I will have to know its API, its integration interface, or maybe if I'm looking for adventures, maybe I want to know the IP address of your database so I can go ahead and ignore your API completely. Doesn't matter. Still, there is some knowledge that has to be exchanged. Now, the more knowledge we are exchanging, the more our components will have to co-evolve. If all I know about your microservice is its API, then you're kind of free to make changes in your implementation details, and it's not going to affect me. If, on the other hand, I ignore your API and go straight ahead to your database, then suddenly a change in your database schema can break the integration. So it will cause a cascading change. So to sum it up, the more knowledge we are sharing, the more cascading changes will follow. That's one dimension. And it's super important. However, what people usually mean when they say coupling or decoupling is another dimension, the dimension of space. Let's say we have two components and we can implement them in the same, let's say, namespace or package, same service, or we can implement those components in two microservices or two different systems. The difference between the two approaches is what is the level of abstraction we are working on. In the first case, when we have them in the same service, the distance between the source code of the two components is located close to each other, right? In the second case, when we have two microservices, then suddenly we have larger distance between source codes. Now we have even different life cycles. Maybe we even have different people in charge of those components. So we have that dimension of space. Usually, when the people say that they want to decouple things, what they mean is let's take a monolith, small distance, and break it apart into microservices, increase the distance. Now, what's going to happen if we do that? It depends on how knowledge is being exchanged across those distances. At this stage, I can give you an answer to your question about whether it's good or bad. So let's say that we are sharing lots of knowledge. And we are sharing lots of knowledge across, let's start with small distance. So in this case, we will have lots of cascading changes, but the components are located close to each other. So it's as if we are modifying one component. Now, the question is, why are we sharing lots of knowledge? And the answer depends on your question about that business context. Do we really need to share that knowledge? In some cases, we have to, because let's say that we have two components that are implementing closely related business functionalities. They have to share knowledge. That's how business affects our design. If, on the other hand, according to the business requirements, we don't really have to share that knowledge, then that design is bad. Then suddenly we're introducing accidental complexities.
Okay,
And
so from the business perspective, it means that coupling and this level of abstraction, we should judge it from the business perspective. Like, do we model the business appropriately in our software, and the degree to which this model is correct will define if our coupling is bad or good, right?
yeah, so
Is it the thought?
yeah, so to evaluate design of interaction of coupling, we have to evaluate the amount of knowledge that is being shared. And that amount of knowledge should always be minimized. However, in some cases, it cannot be minimized because of business requirements. So business affects the design at this stage. It affects how much knowledge has to be exchanged across component boundaries. Second is distance, and the third one is the third dimension is the dimension of the rate of changes. How frequently our components are going to change. And it is also affected by the business because some components of system will get way more attention from the business than others. Business is interested in optimizing, in improving the components that bring benefits to the business, or in other words, money. So yeah, business plays a significant role here in the design of coupling. First, in the way we are sharing knowledge, and the second is the rate of changes of the components.
Okay, thanks. So this is what coupling is about, right? So the amount of knowledge that is shared between the components, and again, we judge this based on how it reflects on the business. Great. Uh, let's talk about distance. So you mentioned a couple of times like this physical distance between the components. Are they the members of the same namespace or the same application, or they belong to different components with different life cycle? Uh, how do we treat the distance in the first place? Well, like for example, I'm a programmer. I need to decide, should I place this bunch of new functionality like far away from the current service, or from current module, or like pick something different?
Mhm. Like consultants proclaim, it depends.
Yeah.
Yeah, so the point of this model is that these three dimensions of integration strength, the amount of knowledge that is being exchanged, distance, and the volatility, they balance each other. You cannot optimize one of them without the context of the other two values. So first of all, let's assume that you have two components and you minimize the knowledge that is being shared between them. According to your business domain, you found that that's the minimum level I have to share. So you are on that minimal level. And it can be low, it can be high. Again, depends on your business. And now you are asking, how do I make a decision about the distance? Should I put them close to each other or can I spread them far apart? So let's talk about it. Let's say that we have two components and they are not sharing lots of knowledge. Let's say that the amount of knowledge that is being exchanged there is really minimal. So what do we prefer, big distance or small distance?
Well, it depends on the life cycle of the components, right? So we should know if the components are changing together or they have different cycles. And
So
in the first case, we want to minimize the distance because like they are changing together. But in the second case, like no, why would I need to redeploy another component if I changed only a single one?
yeah, exactly. And here we getting back to the notion of knowledge, because if they're sharing lots of knowledge, then they will have to change together. If they're not sharing much knowledge, then they won't have to change together. So in the case of minimal knowledge, we want to spread them apart because we can evolve each one of them independently without causing the second one to be redeployed as well. That's what we usually call loose coupling. If, on the other hand, those two components have to share lots of knowledge, probably because they're implementing some closely related business functionalities.
Mm-hmm.
And there is no way for us to reduce that knowledge. In that case, we know that these components will have to change together. So, to make our lives easier in the future, we are interested in co-locating them, putting them close to each other, so that when we'll have to change them simultaneously, at least we won't have to look all over the system to find that other part of the system we have to change. We'll put them close to each other. And when we're putting things that are changing together close to each other, that's what we usually call high cohesion. So on the one hand, we have low knowledge, high distance. On the other hand, we have high knowledge, low distance. Those two dimensions balance each other out. Now, what's going to happen if we do the opposite? If we have components that are sharing lots of knowledge and we're distancing them apart. So both knowledge is high and distance is high. In that case, what we'll get is pain.
Distributed coprolite.
Yes, distributed corporally. Yeah. Yeah, we'll get pain because we'll have to change them frequently together.
Mm-hmm.
They're located far apart from each other. Maybe even different teams are in charge of them. So orchestrating those changes is going to be painful.
Yeah, and this
So
is what you call order coupling, if I'm not mistaken, in your book. That you will need to deploy the services one by one because they are actually coupled, right?
mm, so this kind of relationship I call global complexity.
Mm-hmm.
So it's complexity of the overarching system and complexity because such a relationship increases the cognitive load you are going to experience in order to make changes in the system.
Mm-hmm.
Again, short way to say it, pain. Such a relationship increases pain. Now, what about the fourth relationship? When we have low amount of knowledge and low distance, is this a good relationship or a bad one? That's a tricky question because at conferences, I usually ask this question, and there is equilibrium in the audience. 50% say this is good, other 50% say this is bad. Now, this is tricky because if all we have is two components and they're not really related to each other because they're not sharing lots of knowledge, we have minimal amount of knowledge that's being shared, we're putting them together. If it's only two, who cares, right?
Mm-hmm.
But usually, we are building systems that are more complicated than that. They're not, they include more than two components. What if we have 10, 50, 100 components that are not related to each other, but are co-located in the same boundary? And one day you will have to make a change in the system, and that change is going to affect one of them. Suddenly, you have to find your way through all those unrelated components to find the one you have to change. And once you make the change, then suddenly you have to redeploy all the rest because they're in the same physical boundary. Well, not fun. Again, cognitive load, again, complexity. This time it's going to be local complexity, and it's something that we better avoid. So we have four
Okay.
relationships. One
Hmm.
is loose coupling, the second one is high cohesion, and we have two types of complexities, global complexity and local complexity, but they can also be called a tight coupling and low cohesion, whatever you prefer. It is all a function of those two variables.
Okay. So in order to minimize the pain and maintenance efforts, we need to maximize the local complexity and hide the business complexity there, having the overall system simple.
Well,
That's the recipe. How to avoid this failures that you mentioned
no,
at
no,
the
no, no, no,
beginning.
no. You want to minimize complexities, both local and global. Both are
Okay.
bad. Both are going to bite you in the end. So what you want to do is you want to maximize the cohesion, and you do that, but by only collocating things that are related to each other, where you have knowledge that has to be shared. So in that case, you're putting those things in the same boundary. If
Okay.
they're not sharing knowledge, spread them apart. And that way you will have a loose coupling between the components. Now, there is third dimension of volatility, which is kind of a dimension of pragmatism. And here, if we have, let's say, lots of knowledge being exchanged across a vast distance. On paper, it sounds bad, bad design. However, if those components are not going to change ever, then who cares? That complexity is going to bite us when we'll have to modify the system, when we'll have to introduce changes. So if we can evaluate the expected rate of changes of the components, and we can say that they're not going to change ever, or maybe super rarely, in that case, we can round some corners. And if needed, certain parts
But
of the
that
system,
that's that's impossible in practice. You never know. Like
well,
for the 15 years of my career, like that's the question that you want to ask and get some kind of like reliable answer, and you're never gonna get it. Like predict the rate of changes to a particular module is like seeing into the future. That's impossible. You can just, make some big bets, but like reliably predict it, it's very hard.
absolutely. You cannot look at source code and judging by the source code say that this is not going to change. It's not going to work. However, you take a step back and think about the business, then you can get some insights about the expected rate of changes. And now I have to wear my DDD hat, and there are different subdomains. Core subdomains are going to change frequently. Supporting subdomains are going to change rarely. Generic subdomains depends. So now you have a way of evaluating a rate, the expected rate of changes. Also, almost in any enterprise, there is this legacy system that works, but people are afraid to touch it. Nobody wants to change it. So that's another case when you're integrating with a legacy system that is never going to be changed. That's another case where it's okay to introduce a dependency on its implementation details because otherwise you will have to be that hero that goes ahead and modifies it.
Yeah, but that's exactly what happened in Microsoft. Because, for example, a lot of games rely on some weird behaviors of the underlying platform, like OpenGL drivers and other components. So Microsoft doesn't patch them because it will break games. So it's like the coupling that like you're right on the implementation details, right? You know that this particular thing behaves very strangely, but you kind of use it as a hack. So
Well, I don't know. I use PlayStation.
yeah, all right. All right, got it. Uh, I wanted to ask about the connection between the software coupling and the socio-technical design. We were discussing social technical architecture with Evgeny Nebesov in the previous interview. I will give the link in this corner, I think. But how those things are related? How the coupling between the systems and services affect the design of our teams?
Strongly. So here's the thing, that dimension of space. Up until now, I only mentioned the physical space across source codes of components, right? But there are other things that affect it. And one of those things is the structure of the organization that implements those components. Let's take, for example, let's say we have two microservices. We have two microservices, which means that we have a significant distance between them.
Mm-hmm.
We have different physical boundaries, we have probably different life cycles, etc. However, let's compare this design to another one. And in the second design, we have those two components implemented in two microservices. Again, two microservices. However, in the previous case, both microservices are implemented by the same team. In the second case, we have different teams in charge of those microservices. Now, in the second case, we'll have much higher effort that we'll have to invest in order to implement a change that affects both components. Because now we have to introduce those collaboration efforts. We have to introduce communication efforts. So effectively, in the second case, once we consider the organizational structure, we have greater distance between the components. How it affects us? Well, it affects the dimension of space. The greater the distance, the smaller the knowledge we can allow ourselves to expose across their boundaries. So it is all very connected. And if you are mentioning our shared friends here, then I have a talk that I'm doing with Sonia Natanzan about this topic, but we're doing a collaboration. I am talking about software design, and she talks about how the same principles apply to organizational design as well.
Okay, I am eager to watch it. So we will include the links down below the video. So yeah. Um, all right. So basically, you say that some kind of the organization structure can be perceived as a measure of distance between the components. So it's not only going to the different code base to change something, it's also going to a different team and convincing them to make the change. So that's the distance dimension.
Yeah. So when I'm introducing this topic of distance at conferences, I cannot allow myself to drill down into everything that is going to affect distance. So I'm only talking about, the distance between source code because that's something that is really easy for software engineers to understand. However, in the book, there is this second aspect, organizational design, that affects the distance, and also third one, which is the runtime dependencies, how these components are integrated uh, during the runtime, whether it's synchronous or asynchronous integration. It also affects distance.
All right. You mentioned several characteristics or metrics that we can talk about, the cohesion, coupling, distance, volatility, and so on. Do we have any instruments that we can feed our code bases into and get those metrics to have some insights?
Well, the moment we'll have those tools, we'll lose our jobs. Like that's going to be the end of it.
Really? Not AI is gonna kill development?
That's going to be AI. Yes. Yeah. So look, when you're looking at source code, so One aspect of distance is pretty easy to evaluate. If you have different um, logical boundaries like modules, namespaces, packages, whatever, it's easy to evaluate the distance. Organizational design makes it more complicated. Runtime dependencies, kind of easy as well. The problematic dimensions are strength and volatility, because with strength, when we have to evaluate the amount of knowledge that is being exchanged, it's not enough to count the number of variables exposed across the boundaries. It's also important to understand the semantic meaning of those values, what they are supposed to reflect. Are they reflecting an integration interface or an implementation detail? Those are two different kinds of knowledge with different implications. Same is true for volatility. On the one hand, you can say, I will look at the code base, and if that module never changes, I will assume that its volatility is low. Well, it doesn't work like that. First of all, code lies. Maybe it never changes because people are afraid to touch it, but the business wants to change it. And as I mentioned before, in order to understand volatility, we have to step away from the code and to analyze the business domain. That's something that LLM probably will be able to do it. But at least right now, we don't have any tools that automate this, so we have our jobs.
I think nobody has yet tailored the LLMs to do precisely this. So, folks, if you're looking for an idea of a project where you can use AI for something system software design related, this is your opportunity. So, build a tool that you can, I don't know, run for the GitHub repository, and it will tell you all these different kinds of things about the modules inside. Why not? Because LLMs essentially can understand this semantics, right? So it won't just analyze the syntaxes and the syntax connection between the parts, but actually try to infer the semantics as well. All right, good. You also already started talking about the connection between the coupling and domain-driven design. How does domain-driven design helps us to evaluate volatility in the software projects?
Yeah, so when we have to evaluate volatility, as you said yourself, we cannot trust a crystal ball to do it for us. We can try, but the results will probably disappoint you. So we have to choose a model that we can trust. Now, there are different ways of doing that. The one that I prefer is domain-driven design's model of subdomains. Basically, the idea is pretty simple. We have business domain of system that we are working on, and we can analyze that business domain and identify subdomains. Subdomains are like business building blocks, business functionalities that the company needs in order to succeed in its overarching business domain to get the value of the overarching business value. Now, those subdomains can be categorized into three types. The first one is core subdomains. That's what provides the company its competitive advantage. That's how the company is making money, so it's going to change frequently. On the other hand, we have supporting subdomains, something that you have to implement because your core subdomain needs it, but there is no competitive advantage there, so it's not going to change as frequently. So again, volatility will be lower. Now, core subdomains are interesting problems, supporting subdomains are boring problems, and the third type of subdomains is the solved problems. Sometimes you have to implement some functionality, but somebody else has already done that for you, and you can use their solution. You can use an open source solution, or you can buy an off-the-shelf product, or you can use something as a service, etc. Something that you don't have to implement yourself. Will it change? Probably not. So we can evaluate the rate of changes based on those subdomains, types of subdomains. Core subdomains will change the most, supporting subdomains will change the least, and somewhere near supporting subdomains are generic subdomains, those solved problems.
Okay, so the key to understanding volatility is basically attributing the software to one of the subdomains.
Yeah.
Okay. That's good insight. All right, I think it's time to the questions from the audience. So I will ask a couple of questions from the chat, and then we will go to the questions that we picked with Vlad as the receivers of the free ebook. So let's start. So the question from the chat, David asking is, I struggle with defining module boundaries. Sometimes I create two modules, but they end up overly dependent on each other. Do you have a process for designing modules components?
Oh, that's a great question. Yeah, so that's I don't want to say read the book, but the problem you are describing sounds like extraneous knowledge is being shared across the boundaries of your modules, basically. So it can be the case of that knowledge being extraneous, something that you can refactor away and make it uh, make your modules less dependent on each other. Or maybe if you cannot refactor that knowledge away, then maybe you need to bring those components closer to each other and relocate them into the same module. So yeah, that's a great question. And the purpose of this model of balanced coupling is to help you to steer your system away from complexity and more towards modularity. For modularity, you need to find those effective module boundaries. Now, if I can give you an advice that is not written in the book, then I would define modularity as being able, when you have to make a change, it should be easy for you to identify what parts of the system should be changed, and a change should be localized in one module. Once you have those two properties, you have good modularity in the system. Now, it's not going to happen if you're sharing extraneous knowledge across module boundaries.
Okay, thanks a lot. I hope it answers the question. Okay, another question. What was the hardest part of writing the book? Except rewriting the chapter for 7 times.
The hardest part of writing a book, I don't know, writing it. So look, when I was writing my previous book, Learning Domain-Driven Design, it was way easier for me because by that time I had already conducted lots and lots of DDD trainings. I already tried different ways of explaining that topic, and I picked one that, in my experience, works best. So all I had to do in learning domain-driven design is take that experience and write it down. That's it. Now, with this book, it was way harder. It was way harder because, on the one hand, in order to explain how to achieve that modularity, I had to touch lots of different topics, and I couldn't do it. I had to find a way to minimize that cognitive load the reader is going to endure during the reading. So it was super hard. And yeah, you know what? I would say that that's the hardest part.
Okay.
Minimizing the reader's cognitive load and finding a way to structure that flow of information.
Okay. Thank you very much. So, thanks a lot, folks. If we will still have time after the after the questions from our contestants, we will try to answer them. But now it's time for people that Vlad and me picked for the ebook voucher. Okay, and the first ebook copy goes to Christopher Siciliano. I hope I pronounced that right. And the question is, does the leak of references consider as intrusive coupling? That would mean that we can have an intrusion via weak public API?
Yeah, so first of all, intrusive coupling is something that we haven't discussed today. It happens when you're sharing, when you're integrating using something that wasn't intended for integrating. For example, your microservice, instead of using its API, I'm going straight to its database. That's intrusive coupling. I'm intruding the boundaries of your service. I'm introducing a dependency on some implementation detail that wasn't intended for it. Now, in this question, I assume the reference means, let's say we have two objects and one of them exposes, let's say, a list or an array, and it's a reference to a collection. Now, a consumer can take values from that array, from that collection, and that's what it is intended to do, but it can also abuse that reference and modify it. And in that case, that's going to be case of intrusive coupling.
All right. Next person. So Ángel del Blanco Aguado. Sorry for my Spanish. So he asks the following. In scenarios when a legacy monolithic system remains central, surrounded by microservices to extend functionality, what strategy do you recommend for managing coupling to ensure both the stability of the core system and the agility of the surrounding services? That should be a hard question.
Yeah, that's a great question. It's and super important one. So here, it's all about that volatility, whether that monolith is going to change or you are letting it die, and instead all new functionalities are implemented in those external microservices or not. Either way, your goal here is to optimize the flow of knowledge because you have high distance, that legacy and external services, that's high distance. So you have to optimize the flow of knowledge. And here, I would say that the pattern that is super important is domain-driven design's anti-corruption layer. That is simple. Sometimes it's really beneficial to put a proxy between that legacy system and your newer microservice. So instead of reaching out to the monolith directly, the request goes through the anti-corruption layer, through that proxy. Why it's important? Because that proxy can encapsulate complexity, poor models, or extraneous knowledge that shouldn't be shared, that comes from that monolith in its boundary. Then that knowledge is not going to be shared with the rest of the system, with those newer microservices. So overall, the system is going to be more modular by introducing those proxies. And that's the answer I can give in 1 minute.
Yeah, great. Thank you very much. And the last question from a guy called Vladimir Ivanov. It's not myself, surprisingly. The question is, since integration strength is difficult to measure automatically, this is what we discussed,
Yeah.
what substitute metrics can you suggest to be able to use the balance formula? How about elements that change together based on Git commits and user stories?
So here's the thing. Yes, integration strength, that type of knowledge that is being shared across boundaries of modules, it's not something that we can evaluate in static code analysis, for example. However, if there would be a shortcut, I would introduce it in the book, believe me. Now, if you're looking at repository, let's say, and you have two modules that either change frequently together or they are not changing together at all, can you assume high relatability, let's say, high strength or low strength? Well, no, because those common changes, they can be a result of poor design. They can, let's say that you are introducing extraneous dependencies, something that could be refactored away. In that case, you will observe shared changes in the repository. And it's something that you should refactor, not something that you should base your future design decisions on. So I would prefer finding a way to train LLMs to identify the integration strength for you. It will be a safer method.
Yeah, another hint, you can build a successful tool to do that and sell it to enterprises. So start building now. All right, we have a couple of more minutes, so then let's try to answer more questions. Question is, a microservice able to connect directly to the database of another microservice raises a bigger issue than intrusive coupling, but more of a security control issue. Do you agree?
Well, security is something that outside the scope of this model, because you can have security issues even with integration through integration contracts. Um, yeah, of course, if you have a database and it is exposed to parties that are not supposed to use it, then yeah, it can be an opportunity for security issues, of course. But again, this model has nothing to do with security, and don't use it for evaluating security issues.
Yeah.
Because this model can point to modular design, but it can still have security issues.
Okay. Another question from Javad Norouzi. How to balance and then measure coupling in an event-driven architecture based on microservices architecture style?
Yeah, so it's the same formula, the same balancing formula, the same 3 dimensions of coupling you have to evaluate. That model can be applied to any level of abstraction. Doesn't matter if you are designing interaction between classes or integration between asynchronous microservices. Doesn't matter. Same principles apply at all levels of abstraction. What is going to be different in this specific case is that you have quite a significant distance because you're talking about microservices, but since they are integrated asynchronously, then we'll have even bigger distance. Why asynchronous integration is bigger distance, I'll need a bit more time to talk about it. Uh, yeah, let's leave it at that.
Yeah.
You'll have to trust me.
Yeah. Okay. Thank you. I think we'll pick the last question and call it a day. So the question from a mobile developer, Nav Singh. So he's asking, what are the metrics for measuring the balance of coupling when modularizing a code base?
Yeah,
Like
so
if you're splitting a monolithic data code base into the components, so how do you achieve lower coupling? How do you measure it?
yeah, so the measure here is on the positive side is what is the modularity of the system, and on the negative side is what is the complexity of the system. Of course, you want to minimize the complexity and increase the modularity. How do you measure them? In what units you're going to measure them? I don't know. It's not something that we as an industry have researched enough. However, this model of balanced coupling gives you a way of evaluating your design decisions, whether something that you want to introduce into the system is going to increase its modularity or is going to increase its complexity. Again, it's function of those 3 dimensions: the integration strength, the amount of knowledge that's being shared. The second one is distance, and the third one is volatility. Once you have those 3 values, you can evaluate what's going to be the end result of that design.
All right. I think that's it for today. Thanks a lot to Vlad for coming to this interview and discussing the balancing coupling in software design and all the metrics and the business impact. Thanks a lot. I learned a lot today. Please write down in the comment section what was the most insightful idea for you. And don't forget to leave a like because it really helps to run the channel. For today, that's all. Thank you very much. Vlad, thanks for coming.
Thank you so much.
Yeah, so read books, educate yourself, and grow. Thank you. Until next time. Bye-bye.
Bye-bye.
Все, стрим закончен.